And now we begin the fourth 9 weeks. I'm sure you're happy to see that. And in these fourth 9 weeks, we're going to talk about waves of different kinds, sound and light, electricity, and magnetism. We're going to start off by talking about periodic motion, waves, and wave behavior. And then a little later, we'll talk more specifically about sound waves and light waves. Are we ready to begin? Here we go. Periodic motion is something that continues to repeat, and waves follow this repeating pattern because the energy does the same kind of motion all the time that the wave moves. Here's your definition of periodic: a repeating pattern. Now we're talking about a repeating pattern of motion when it comes to waves, but many other things are also periodic. As a wave moves, there is an instant where there really is no motion at all, but just such a brief instant that even if we could see the wave, we would never really notice. That's called the rest position, a very brief instant when the wave is not moving at all. Here's your scientific definition of wave: a rhythmic disturbance that transfers energy through matter. Well, you're hearing the sound of my voice. The voice went from me through the air into the recorder on the computer, and now the sound is coming out through the speaker of your computer, through the air and into your ears. The air is the matter, and there are other things involved as well, but basically sound travels through the air, but sound can travel through liquids and solids as well. In fact, even faster than through the air. So a wave is the energy that travels through a matter. And I just talked about a sound wave. Well, light is also energy that travels in a different kind of wave through the air, such as from the sun into the Earth's atmosphere through outer space, and then into our eyes through the air. Rest position, not moving, wave, rhythmic disturbance, transferring energy in a periodic motion or repeating pattern. Ready? Genesis 1, verses 14 through 19 remind us that God made the sun, moon, and stars on day 4 to mark seasons, days, and years. And notice, after the word years, I have periodic cycles. Well, look at the word seasons. What are the seasons? Spring, summer, fall, winter. Now, winter goes from the end of the year into the beginning of the next year. And then what do we have after winter? Spring, then summer, then fall, then winter. And this happens every year. There's a periodic repeating cycle to the 4 seasons. Look at the days: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. And then what happens? You know, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday again. And then Sunday through Saturday again. So the days, they are repeating cycles. And even the years, we could have said the months as well. January through December, and we have a periodic cycle that continues to repeat. The earth revolves around the sun yearly and rotates daily. Now this is actual motion revolving around the sun, and we get the same orbit every year and the same rotation every day. These are repeating patterns called periodic. Seasons are based on the position of the earth in its orbit around the sun, and every year we have spring at the same time of year, we have summer at the same time of year, and the same things with fall and winter. Genesis 1, 14 through 19. Ready? Examining periodic motion. Now, look at the pictures here. First, we have a spring that we would pull down and let go. Now, what will happen when I pull the spring down and let go? I'm sure you already know. The spring will go up. Now let's assume I pull that straight down, not sideways at all. Go straight up, come down and up, and come down and up. Now eventually that spring will stop moving. And the same with this little pendulum over here. Pull back on the ball, let that go. We get the swinging motion back and forth. Eventually we'll get smaller motion until we get a standstill. Now that's because of air resistance. But let's disregard air resistance for a moment and then pull down on the spring. If we let that go and there was no resistant forces to stop that motion, would that motion stop? Of course not. That answer is no. Same with the pendulum. If there was nothing to stop the motion or even slow down the motion, that would also continue indefinitely. The spring will continue to expand and compress. Hold on. Excuse me. And as I've said before, it just shows we're human. And that pendulum on the right side would continue to swing indefinitely because there's no resistant force if we disregard air resistance. The pendulum will continue to swing. It takes a restoring force to keep that oscillation going. Okay, I'm going to grab my meter stick here and act a little like this pendulum here. Now you see I'm holding the stick here. So as I raise this up, you see the repeating motion of the meter stick. Now I am continuing to push and pull on the stick, and as long as I do that, this swing will continue to happen. Okay? But now look, when I stop right here, when I stop pushing and pulling on there, you see that that stick stops moving because I'm no longer applying the restoring force. When I continue to push and pull, we will continue to get that motion. If there's a restoring force that continues providing energy, then the motion will continue in that periodic fashion. Ready? How can we use periodic motion? You ever seen a grandfather clock? Look at the picture there. The pendulum will continuously swing from right to left and left to right. Old style watches and clocks use pendulums and springs, or maybe one of them, to keep time. But there has to be a continuous supply of energy. I'm going to pause for just a moment. Be right back. Of course, on the video, you wouldn't even notice if I didn't say that I paused. But watches and clocks use the pendulums and the springs to keep time. But there's a continuous source of energy, such as a battery for the watch, or maybe the clock is plugged into the wall to get a steady supply of electricity. If there's no force or energy to continue that motion, eventually that motion will stop. Musicians, you may know what a metronome is. These are instruments that help you stay in time, and some of them are pendulums that swing back and forth. Others are more electronic and give a flash of light and a clicking sound. That's a steady rhythm to help you keep time. Now, light and sound come from periodic waves of energy, and we will talk in detail about sound waves pretty soon and light waves a little later on. But light and sound come from the periodic waves of energy. Oop, I hit the stand there, didn't mean to. Oh well, ready? What is a wave? You saw a definition earlier. Well, here's a definition of a wave. A disruption of matter that carries energy from location to another. So that's different wording than what you may have seen before, but it's still the same idea. A wave, a disruption usually sounds like something's going wrong and getting ruined, but that's not necessarily the case. Disruption of matter, scientifically speaking, just means molecules have been moved, and that movement carries the energy from one location to another. In a mechanical wave, that wave moves through the medium, and whatever a wave passes through we call a medium. It must be some kind of matter, and then cause the molecules in that medium to collide. So think of sound waves, and I'll show you a little more in just a little bit. Electromagnetic waves, which is a fancy term for light waves, because they come in what we call the electromagnetic spectrum. Those move through outer space, which is a vacuum, and a vacuum simply means no matter, no air. Sound waves can't move through outer space. There must be some kind of a piece of matter, a medium, in order to carry sound waves. But light waves can move through outer space or a piece of matter. But these are the two main kind of waves. Sound waves are considered mechanical, and light waves are considered electromagnetic because they contain both an electric field and a magnetic field. Ready? Now, all waves have these properties, no matter which kind of wave we're talking about. All waves have what we call frequency, and frequency in general means how often an event happens, and the time part of that frequency could change. But we measure wave frequency in how many waves per second happen, how many sound waves enter your ear, or how many light waves enter your eyes every second. Amplitude, all waves have an amplitude. That's what determines how strong the wave is. The height of a wave, a very tall light wave would be very bright, and a short height of a wave would be a dimmer light. A big amplitude on a sound wave would be a loud sound, and a small amplitude would be a much softer sound. The amplitude determines how strong the wave is. And depending on the kind of wave, there are ways to measure the wave length. In this case, the name tells you the length of the wave. The length between the same parts, and there's the key word right there, same parts on consecutive waves. Now, all waves have a frequency, an amplitude, and a wavelength, but the two different shapes of waves, the names of their parts are different. Ready? Here's what we call a transverse wave. This is what people tend to think of when they think of the word wave. You see the up-down motion as I'm also moving left to right across the screen there. In a transverse wave, such as a light wave, or you can see an ocean wave, well, you honestly don't really see the wave. You see the water acting the way the wave makes the water act. The wave is the actual energy moving through the water, and we see that the energy pushes the water up. And we can see the top of the ocean wave. We don't necessarily see the bottom. However, if we were treading the water here, and the wave comes through our bodies, we get pushed up, then back down, and then back where we started, and maybe a couple of times before we stop bobbing up and down. Light waves travel in this shape called transverse. The top of the wave is called the crest. The bottom is called the trough. Here's the amplitude you saw on the last page, the height of the wave. And this would be the same distance down to the trough as up to the crest. And the wavelength, remember, the same part. So crest to crest on two consecutive waves. Tell you about this guy right here called lambda in a little bit. The energy and the medium are perpendicular. As the energy moves across, let's say horizontally, well, then the matter moves up and down. And that's how we get, see, I'm moving the stick both up and down and side to side at the same time. That's how we get this type of motion. And that makes a transverse wave. The energy is contained in the crest of the wave. So energy here, no energy here, no energy or very, very little energy in the troughs. And the energy continues to constantly go up, down, up, down. That's a transverse wave. The energy and the medium are perpendicular to each other. The energy moves one direction and the molecules of the medium move perpendicular. Ready? In a transverse wave, a slinky, when we're actually in class, is going to show this a lot better than a picture would. But in a longitudinal wave, you see here where molecules get compressed or pushed close together, that's called a compression. Where molecules spread out, that's called a rarefaction. So basically what happens in a sound wave is we get a squeezing and an opening, and a squeezing and an opening as we go across the screen here. Wavelength measures same part from one wave to the next. And notice I'm measuring from the middle of the compression to the middle of the compression to get the wavelength. And rarefaction is the open part. Now amplitude, just like with the transverse, amplitude is how big the crest is. Amplitude of longitudinal is how big the compression is, the size of the compression. Sound waves are longitudinal. Sound waves contain compressions and rarefaction. And again, the bigger the amplitude, the louder the sound, and the smaller the amplitude. Let's say it was only this big, that would be a softer sound. Sound waves have the energy and the medium that are parallel to each other. So as the energy moves across the screen left to right, we get this, I showed you a moment ago, the squeezing, where we get the molecules actually moving in both directions, but parallel could be the same direction, could be opposite, actually a combination of both, but still horizontally across the screen as the energy moves horizontally. The energy is contained in the compression, just like the energy of the transverse wave is contained in the crest. If I go up and down, then the crest at the top contains the energy. In the longitudinal wave, the energy is in the compression. Ready? See the calculator up there. How do we measure waves? Well, let's try it again. We measure the wavelength from crest to crest or from compression to compression. But some terms, you saw this word a moment ago, Waves per second are involved in the different kinds of ways we can measure waves. We use a lowercase f for frequency. Capital F means force. The unit is called a hertz. Now, in order, though, to use hertz, we have to have our time as seconds. So if we see waves per minute, we then have to convert minutes into seconds by multiplying by 60. Or any other difference in time, we have to change to seconds. And hertz, named after a guy whose last name was Hertz. Spell out the whole name with a little h, or kind of like a chemical symbol, big H, little z. That's how we write the unit for frequency. Period, capital T. This is the time taken for one wave to pass through. Frequency is how many waves pass a given point in 1 second, and period is how long does it take for one wave to pass by that point. Turns out these are reciprocals of each other. Since period is time, and in the metric system we typically use seconds to measure time, we'll use seconds to measure periods. Frequency and periods are reciprocals of each other. There's a math term. And I like to say this, recip means flip. 3/4, the reciprocal is 4/3. We simply flip over the fraction. Therefore, the frequency, if I know the period, I just flip over. So if the period is 5 seconds, the frequency is 1/5, or 1/5 of a second. Same idea with the period. If I know the frequency is 20 hertz, 20 waves per second, then the period is 1/20th of a second. And that's really all there is to it. If you know 1, write it as a fraction and flip the fraction over. Ready? Again, you see a calculator. Now we're going to figure out how to calculate the speed of a wave. Speed equals wavelength times frequency. There you go in words. And remember, in physics, we use a lowercase v, velocity, for speed. Actually, because waves travel in directions, so waves are also vectors. Velocity equals wavelength times frequency. This guy right here, told you earlier, I'll tell you about in a little later. Well, now it's a little later. Kind of looks like an upside down Y. The name of this symbol is lambda. The meaning is wavelength. We use lambda in the equation. We do not use a W. No W. Don't put V equals WF. I will mark you off for that. V equals lambda F. The name of this is lambda, a Greek letter. The meaning is wavelength. So speed equals wavelength times frequency. And we'll do practice problems with these. And just like with the forces, if I know the speed and I know the wavelength, I will divide to get frequency. Or I will divide if I need to figure out the wavelength. I'll do speed divided by frequency to get wavelength. Ready? Okay, reflection. Watch this. Reflection means bouncing off a surface. Now, not just like this and bounce up. What happens here is the wave comes into the surface. The green is the surface, and hits and flips over and then comes off the surface. Now, of course, much faster than what I just showed you. If all the energy reflects, the amplitude is going to remain the same. Question is, will every bit of energy bounce off that surface? And the answer is no. At least a tiny amount will be absorbed into the surface. So the amplitude will shrink at least a little bit depending on the surface and the kind of energy. Could reduce a lot, again, depending on the surface and the energy. But if all energy reflects, the amplitude would remain the same and the sound would never go away. But we know that with an echo, we do lose a sound. We don't get echo, 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 echo and stay the same. The echo would never go away. We get echo, 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 echo. And eventually the sound fades away because every time the sound wave hits the surface absorbs some of that energy, meaning the amplitude shrinks, and eventually all the energy will leave the wave and no more sound. But reflection is simply bouncing off a surface, but one more time, notice flips direction, come in, hit the surface, flip over, and come off. That's what sound waves do. And lab activities that we'll do in class, we'll be able to see that simply by using a slinky. Ready? All right, here's something else about waves called refraction. Now this a lot easier to think of with a light wave. We have a wave coming in here. This may be the air, maybe this is a fish tank. So we have some glass and some water inside the tank. The light wave enters at this angle, and notice how the wave bends inward a little bit. See, this line's perpendicular, would go across. And we have the line, we have the line bending inward and then coming out back into the air and bending outward again to what will be the same angle. You ever seen in a fish tank, you think the fish is in one spot, but the fish is actually in another spot. Now the fish may actually be up here, but because of the bending of the wave, the fish appears to be over here. So if you were to try to reach in and grab, most likely you'd miss because you didn't account for the refraction. Refraction is bending as the wave passes into a new medium. So again, air, glass, and water are both denser than air. The wave will bend inward toward the perpendicular line, which we call normal. And then when it comes back out to the air on the other side, go back to the original angle, but you notice that that has been shifted a little bit. The wave will also change speeds. And in light slows down when going from a less dense to a denser material. And with sound waves get faster when they go from less dense to a denser material. So they kind of do opposites in that regard. But both will bend unless there's an absolute perfect perpendicular entrance into the new medium. The denser medium slows down the wave if it's a light wave. The less dense speeds up the wave if it's a light wave. For sound waves, that's actually opposite. But refraction is bending of the wave as the wave passes into a new medium. Both speed and direction change. Ready? All right, here's diffraction. Okay, you see the wave, and there's a wall. And the wave is going to hit this wall or barrier with a tiny opening there. Think back to when we talked about pressure and the water coming through the end of the hose, and I even had a picture of this in the notes. If you just let the water come out of the end of the hose, the water may just go down, and not very fast, not very far. But put your thumb at the end of the hose, then the water shoots faster and further before being pulled down to the ground. That's diffraction. Waves spread out when passing through an opening or around an edge. The pressure of getting a larger wave through a smaller opening will force that wave to come through much more forcefully and allow the wave to spread out more and go faster. The larger the wavelength and the smaller the opening, the more diffraction will occur because of the pressure pushing that bigger wave through a smaller opening, just like the water through the end of the hose with your thumb at the end or the nozzle that we talked about before. So diffraction occurs when waves spread out while passing through an opening or around an edge. So maybe around this end of the wall and this end of the wall. Ready? Now, interference is a term that sounds like something went wrong and things got ruined. Well, in waves, that's not necessarily the case. Interference is simply two or more waves passing through each other. Okay, let's think of a sound. You ever get the staticky sound? You try to tune into a radio station, well, especially older ones. It's a lot easier now digitally, but we had to turn the dial. If you didn't get right on the correct frequency, you get that staticky kind of sound. Maybe hear the music, but with that sound in the background. Well, what's happening here? Now, light waves are actually this shape, but let's pretend they're sound waves for a moment. You have two waves that come together, they're identical. So maybe you have two radios on the same station and you point the two radios toward each other. Identical sound waves, the compressions, these are actually crests, but we're calling them compressions now. They're the same and they match and they meet up and hit each other. They're going to build to this bigger one here. So we have little plus little equals big, and that big is twice as much as either one of these two. We have what's called constructive interference, in which the same parts of two identical waves hit and join each other. That's going to build and strengthen the wave, so that sound would be louder and a lot more clearer. And two light waves that do constructive interference, the crests meet and get a bigger crest with a bigger amplitude, so that light becomes brighter. Now the opposite is destructive, and that's typically what people think of when they hear the word interference, things getting ruined. Destructive interference happens when the crest of a light wave meets with the trough, or the compression meets with a rarefaction of a sound wave, and then the amplitudes mathematically shrink. And because the amplitudes become smaller, the energy is less. So the light wave becomes dimmer and the sound wave becomes softer. Now this picture shows a complete cancellation because two perfectly identical waves meet a crest and a trough exactly just right and get a complete cancellation to where there's no more wave. That means no more light or no more sound. That doesn't happen a whole lot. Usually we get close to but not exact matchups, so we get a staticky sound or a really dim light. But interference is simply waves that pass through each other, and it can be either constructive or destructive based on how the parts collide. Ready? Okay, Doppler effect. Look at the wave here. Again, this is really not longitudinal, but it's easy to use for demonstration. You ever stand outside and you hear a car approaching and then the car passes by? This is the sound that we hear, something like this. We get a gradual buildup of the sound, the pitch and the volume as the distant object, in this case the car, approaches. The sound gets gradually louder and higher pitched. And once the car passes our ears, we get that very quick fade away. So let's do that again. The effect is the waves as the car is approaching are getting crushed together. That's what our ears perceive. And because the frequency increased, the pitch increased. With a sound wave, the higher the frequency, the higher the pitch. And as the car passed, look what happened to the wave. The wave got stretched out to a longer length, which means a smaller frequency. And that happened very quickly, and so we got that fade off of the pitch from very high to very low very quickly. And then the volume, of course the car's going away from us fast, the volume will go down. So one more time, probably laugh at it. So a gradual buildup of volume and pitch and a quick fade away. Ready? And that is all. Wave bye-bye. Next time we'll talk a lot more about sound waves. See you then.